Hello everybody, in this lecture we will be solving 1994 IMO problem number 2. Here's a view of this problem. We're given an isosceles triangle ABC where AB is equal to AC, like that. BC, AB is equal to AC. Suppose that M is the midpoint of BC. No wonder that, so this point M is the foot of the altitude from point A. And also point O is on AM such that AC is perpendicular. So this is a 90-degree angle here. And similarly, because of the symmetry, we would have, okay, yes. So that's our point O here. So similarly, we have also AB is perpendicular to OB. Q is an arbitrary point on BC. So let's say Q is here. And E lies on AB and F lies on AC such that EQF are collinear. So I just extend AC here and I just pick my points. Let me change color here. Let's pick the red color. So I'll just pick the points such that there you are. Okay, so we have point E here and point F on AC. And finally, so these 3 points E, Q, F are collinear. Finally, prove that OQ is perpendicular to EF. So let's also draw OQ. Okay, so OQ is perpendicular to EF if and only if QE and QF are equivalent. So let's start with this direction. So we want to prove this direction, suggesting that let OQ be perpendicular to EF. So therefore, this is a 90-degree angle here. As a result, the points, the circle with diameter OE would go through the points B and Q as well, suggesting that points E, B, OQ are cyclic. Let me go ahead and draw this circle here, like that. Here, OE is the diameter of that circle, so let me go ahead and also draw that diameter as well. Okay, good. And in a similar way, consider the circle with diameter OF. Similarly, Q and C are on that circle as well. So we have OQCF cyclic. Let me also draw that circle as well. So with diameter OF. And now we are ready to do some angle chasing. Let's quickly chase some angles here. So notice that this angle here is equivalent to this angle because they both subtend the arc OQ on the first circle here. In a similar way, this angle here is equal to that angle because on the second circle, they also subtend the arc OQ. Finally, notice that OM is a perpendicular bisector to BC because M is the midpoint of BC because it's the altitude of an isosceles triangle ABC. As a result, angle, so let me write that down, angle CBO is equivalent to angle BCO, suggesting that in fact, so therefore those two angles are equal, so this type of angle is actually equal to that type of, so this implies that angle OEF is in fact also equal to, so this angle here is also equal to that angle EFO or OFE. But then this implies triangle EOF is isosceles triangle and OQ is the altitude of that triangle, and in an isosceles triangle altitude it would immediately imply the desired result that EQ must be equal to QF. So we have just proved one direction. Now let's prove the other direction as well. Let me redraw the picture like this. Let's open some space here. I drop an altitude here. That's the point M. I extend that point. I draw a perpendicular here. That's 90 degrees. Remember our triangle ABC. It meets here at O. And then that's also 90 degrees. Furthermore, we have the point Q. This time I don't know the angle, but I know that QE is equal to QF in that occasion. So that's my point Q. Let's consider this line, I guess, like that. Oops, probably it should go like this. Yes, so that's the point F here on AC, and that's the point E. And we know that EQ is equal to QF now. So what I will do is I will, well, obviously we don't know if OQ is perpendicular to EF yet. So what I will do is I will draw a perpendicular line to OQ now. So let me go ahead and do that because I don't know if that's really perpendicular or not. So let's assume that this is in fact the perpendicular line. So this angle here is 90 degrees. Let's call it E prime, and let's call this point as F prime. So I'm suggesting here that angle E prime QO is equal to angle F prime QO. So my goal would be to show that in fact the point E prime and E are coinciding, right? So you can think of E prime and F prime as phantom points. By the first part of the proof, because OQ is perpendicular to F prime, E prime F prime, we already have proved that E prime Q must be equal to Q F prime from the first part of the proof. So this implies that E prime Q is equal to Q F prime. And now when you look closely, and so therefore this is equal to that. Now when you look at closely to the line segments EF and E prime F prime, we realize that these two, they bisect each other, right? They intersect at their midpoints, implying that bisect each other. So implying that in fact E prime F prime is a parallelogram, because this can only happen for a parallelogram. But then that can't be the case, because we already know that EE prime is part of is a line segment on the larger line segment AB, and FF prime is a line segment on the larger lines AC. But those two lines AB and AC are not parallel to each other. So the only way that this can hold EE prime FF prime be a parallelogram is if it's in fact a degenerate parallelogram, right? So therefore E is in fact equal to E prime, and F also is in fact equal to F prime, and that solves the problem. Again, that implies that OQ is in fact perpendicular to EF as a result. Okay, so that was awesome. I would like to provide an alternative proof to this problem in the next video. So in that proof I will be using inversion. So if you would like to enjoy another proof, please feel free to tune in for the next video.